What is the engine of life? For our entire history, we have had only one answer: the sun. It is the great unwavering truth of our world, a cascade of energy that begins with a single simple process. Photosynthesis, the mechanism that turns light into life. It is the foundation of everything we see: the grass, the forests, the phytoplankton, which feed the grazers, which feed the predators, which feed us. This solar-powered food web is so fundamental, we consider it a biological absolute. So what happens when the sun vanishes? What happens when you descend past 1,000 meters, past the last photons, into a realm of total darkness, a place of crushing pressure and freezing cold? By all the rules we know, this realm should be a void. It should be a barren biological desert. This is the root of our thalassophobia, the fear of an empty, crushing, and lifeless abyss. But what if the rules are wrong? What if life found another way, a separate alien genesis hidden in the dark? Now, let's dive into the data and uncover the reality hidden in the deep. This is the rule. It is the most fundamental transaction on Earth, but how does this solar engine actually work? It begins with a pigment, chlorophyll. It is a molecule designed to trap a photon of light. That captured energy is used to power a reaction. It takes 6 molecules of carbon dioxide and 6 molecules of water, and in the presence of sunlight, it forges them into a single molecule of sugar. Glucose. The fuel for almost all life. The byproduct, of course, is the oxygen we are breathing right now. This single elegant chemical reaction is the architect of our entire biosphere. From this one process, the great trophic pyramid is built. Level 1, the producers, the plants and algae. Level 2, the primary consumers, the herbivores that eat the plants. Level 3, the secondary consumers, the carnivores, and so on, up the chain. But every single link in that chain traces its energy back to the sun. When we analyze the deep ocean, this rule seems to hold, though in a tragic, diluted form. The deep is a world of pure consumers. Nothing down there can produce its own food. It is a realm of scavengers, waiting for the scraps to fall from the sunlit world above. We call it marine snow, a slow, constant drizzle of decaying plankton, fish scales, fecal matter, and dust. It is a meager, low-energy fallout, a thin, starving link to the photosynthetic engine. For decades, we believed this was the only energy source sustaining the abyss. This belief painted a picture of the deep as a slow, barren, and desperate place, a biological wasteland, where life clings on but cannot thrive. It confirmed our deepest fears, that the dark is a place of absence, of starvation. This was our rigid, unassailable understanding of biology, and it would have remained so if we hadn't pointed our instruments at the very last place we expected to find life at all. Then, in 1977, we found the impossible. The deep-sea submersible Alvin was diving 2,500 meters. Exploring the Galapagos Rift, scientists were looking for geology, not biology. They were searching for warm water springs, evidence of tectonic activity on the seafloor. What they found was not a barren, rocky plain. It was a forest, a dense, thriving, spectacular oasis of life. Giant tube worms, 6 feet tall with blood-red plumes, massive clams, the size of dinner plates, and swarms of ghostly white crabs crawling over everything. This should not exist. It was a complete and total paradox. This ecosystem was dense. It had the biomass of a shallow water coral reef, but it was in total darkness. There was no sunlight. And it was located miles from any significant source of marine snow. The energy falling from above was nowhere near enough to support this sheer amount of life. It was like finding a bustling city in the middle of the Antarctic, with no food, no fuel, and no supply lines. The discovery posed the single greatest biological question of the 20th century. If they were not eating the snow from above, what on earth were they eating? The answer was not falling from above, it was rising from below. The water itself was the key. The warm springs the researchers were looking for were actually volcanic chimneys known as hydrothermal vents. They were superheating seawater to over 400 degrees Celsius and infusing it with a toxic cocktail of chemicals leached directly from the planet's crust. And one chemical in particular was abundant: hydrogen sulfide. To us, it is a poison, the smell of rotten eggs, deadly. But to the life here, it was something else entirely. It was the fuel. Researchers collected samples and found the water was thick with microbes, bacteria, and archaea. And when we analyzed them, we found they were doing the impossible. They were not using light to make food. They were using the chemical energy stored inside the hydrogen sulfide. This was the antidote to our fear, the answer to the paradox, the reason the void was not a void. We gave this new process a name: chemosynthesis. It is a process as profound as photosynthesis, but built for the dark. It does not use a pigment like chlorophyll. It uses specialized enzymes to break the chemical bonds in the sulfide molecule and harvest the energy released. It takes hydrogen sulfide, water, and carbon dioxide, and from that toxic volcanic soup, it forges sugar. It creates life from chemistry. This single discovery tore up our entire understanding of biology. It proved, definitively, that the sun is not the only engine. These microbes, these chemoautotrophs, they are the producers of the deep. They are the plants of this dark forest. They form the base of an entirely new alien food web, one that is completely independent of the sun. But what about the animals? The giant tube worms? They have no mouth, no stomach, no gut. They do not eat in any way we recognize. Instead, they are a perfect example of symbiosis. Their bodies are packed with these chemosynthetic bacteria. The worm's red plume is a specialized gill. It absorbs the hydrogen sulfide from the vent and oxygen from the ambient seawater and delivers both chemicals safely to its bacterial partners. The bacteria perform chemosynthesis inside the worm's body, and the worm lives entirely off the sugar, the glucose, that its partners produce. It is not an animal, it is a living chemical reactor. The clams, the mussels, the crabs, they either filter feed on the free-floating bacteria or graze on the thick bacterial mats that cover every rock. This is not a world of scavengers waiting for scraps. It is a primary production zone, a self-sustaining, self-contained, lightless cradle where life is not surviving, it is thriving. Sunlight and sulfide. These are the two engines, two different blueprints for building a biosphere. Photosynthesis, the one we know, is a top-down system. It relies on energy arriving from an external source, the sun. This energy is most intense at the surface, so life clusters there, in the light. The entire system is widespread, visible, and spread thin, across the entire face of the planet. Chemosynthesis is the opposite. It is a bottom-up system. It relies on energy emerging from an internal source, the planet itself. The fuel is not light, it is geology, heat, minerals, and chemical reactions. This energy is not widespread, it is hyperconcentrated. It emerges only at specific, volatile points, at tectonic seams, at cold seeps, at hydrothermal vents. So life does not spread out. It clusters in tightly, forming dense, isolated islands of extreme biomass. This comparison is the final antidote to our thalassophobia, because it exposes the flaw in our most basic assumption. We feared the deep, because we defined life by our own engine. We are creatures of the sun. We looked into the darkness and saw only absence, the absence of light, the absence of plants, the absence of food. We saw a void, but we were looking for the wrong thing. The deep is not an absence, it is a presence, the presence of immense chemical potential. The abyss is not a barren desert, it is a chemical battery charged by the Earth's core. The life here is not monstrous or alien, it is the most logical, elegant, and efficient solution to an environment we simply failed to understand. The pale crabs, the blood-red worms, the ghostly bacterial mats are not making do. They are not desperate scavengers. They are primary producers in a system that is, in many ways, more robust than our own. Think about our solar engine. Photosynthesis is fragile. It is vulnerable to seasons, to weather, to night. It can be shut down by a volcanic ash cloud or a single catastrophic asteroid impact. The chemosynthetic engine does not care about the surface. It is powered by the steady, predictable heat of the planet. It runs in total darkness 24 hours a day for thousands, perhaps millions of years, completely insulated from the chaos of the sunlit world. This isn't just a biological curiosity, it is a parallel evolutionary path, one that may have even come first. This is the true implication, the shift from fear to awe. The deep is not a grave where life goes to die, it is a bunker where life endures. This is the true lesson of the deep. The discovery of chemosynthesis was more than just a new chapter in biology. It was a correction. It forced us to confront the limits of our own solar-centric perspective. The abyss is not a monster. We simply misunderstood the rules. Our thalassophobia, our primal fear of the dark, crushing water, was born from an assumption of absence. We looked down, and all we could see was the end of our own world. We failed to imagine that in that same darkness, an entirely different world, with an entirely different engine, could be beginning. The deep is not a void, it is a chemical cradle, powered by the very heat of our planet's formation, and this realization has profound implications, far beyond our own ocean. If life can thrive here, in total darkness, on a diet of toxic chemicals, then where else in the universe might it exist? On moons like Europa, beneath its frozen crust, where we suspect a warm, mineral-rich ocean is being heated by the same tidal friction. If life needs only water and chemical energy, then the habitable zone is not just a thin, sunlit band. The dark, deep oceans of the cosmos may be the most common cradles of life, and our own planet holds the blueprint. The deep sea is not an alien world. It is perhaps the most elemental part of our own. It is not a place of death. It is a testament to life's profound chemical and unbreakable ingenuity. It is not a place to fear. It is a place to find awe.